So in the addition polymerization reaction, it is forming a synthetic polymer, which is a plastic called polyethylene. So it is a polymer of ethylene monomers. And so the monomer is just a very simple molecule. It's 2 carbons and 4 hydrogens. So you basically take this monomer and bond it over and over and over and over again in the hundreds or thousands. And that's the starting point of 2 of the main plastics that you have around the house. An example being this standard plastic water bottle is a polyethylene. Okay, so let's take a look at the reaction when you have the monomer. The ethylene monomer is 2 carbons, and this is the starting point of the ethylene monomer. It's 2 carbons, but it also has 4 hydrogens. So let's add those 4 hydrogens. Here's 1, 2, 3, 4. So here's the Lewis structure of the ethylene monomer. You've got 2 carbons and 4 hydrogens. And here, this shows the bonds. You have those 2 carbons share 4 electrons. That's a double bond, okay? Because remember, a single bond is 2 electrons shared. And a double bond is 4 electrons shared between the two atoms in the bond. And so this is the 2 carbons. And then there are the 4 hydrogens. These are the white atoms. And then each individual carbon, here's this carbon on the left. This obeys the octet rule because you could count 2, 4, 6, 8 electrons around it. Each individual hydrogen obeys the duet rule. Being in that bond is 2 electrons. So this is the ethylene monomer. It starts off with 2 carbons and 4 hydrogens. Okay, and so we just built the monomer, and then we're going to continue on and build the polymer. Hold on a second. Let me find that. No. Okay, so this is the first of today's worksheets. Instead of building that polymer on that actively on that screen, we're going to build it on the worksheet. So this is 9.1 lecture worksheets. And we're just going to start with this first top of the worksheet. So it's called addition polymerization. In the addition polymerization reaction, you have 1 monomer added at a time to one side of the polymer chain. So this is forming the polymer, and eventually you'll have a lot of monomers, and that will be a giant molecule called a macromolecule. So that's a giant molecule, but it really is very simple at its core. It's the same thing bonded over and over again, and that same thing is the monomer. So you just have to have a soup of monomer, just this one homogeneous monomer, and it just bonds over and over again, okay? So this is the formation of the synthetic polymer that is most of the plastics we have in our everyday life. Is you start with a monomer and you just stick them all together. So this is not simple in sticking it together like tape. It is the addition polymerization is a process where you start with a monomer like ethylene. So we just built the monomer ethylene, and this is the same structure, 2 carbons with a double bond. So notice that double bond that I just wrote over it in blue. And in forming the polymer, this double bond breaks and becomes a single bond. Okay, so this becomes a single bond in the polymer. And this is important because carbon can only have 8 electrons in the octet rule. So this is 8 electrons here in the monomer, but in order to still have only 8 electrons and not more and not less, this has to become a single bond. And this allows for bonding on either side of the monomer as single bonds. So there are the still it still has in the monomer the same 4 hydrogens. So 1, 2, 3, 4, and those 4 hydrogens are still there. And what you have in the polyethylene is that this is bonded on either side. To these ethylene monomers. Okay, so the most important thing though is that double bond becomes a single bond in the polymer. So in the monomer, it was a double bond, but it becomes a single bond in the polymer. Other important difference is that the number of monomers that are present at the beginning is represented at the end in the polymer as a subscript. And so this is the third thing, which is this R is the reactive catalyst that initiates this reaction in the first place. And you notice it has that dot, that is a single unpaired electron. And so let's take a look at drawing the structure of the polyethylene that's composed of 5 ethylene monomers. So we need 5 ethylene monomers. So I'm going to start with that N is equal to 5. We need 5 of them. So this is 5. And just copy the structure of that ethylene monomer, which is the carbon double bond to another carbon. And then there's, okay, so this is going to be the preliminary version, which is just copying that top, this top reaction. So what happens is the carbon forms a single bond and it's no longer a double bond, and that there are still the 4 hydrogens. And then there's going to be 5 monomers in there. And so this is going to be 5 of these is the first one I'm going to draw in blue. And so this is 2 carbons with 4 hydrogens, and there are single bonds coming out of each carbon. So that's the first monomer. And then the next monomer I'm going to do in purple. So this is 2 carbons with 4 hydrogens. And notice those are all single bonds between the carbons and single bonds between to the next monomer and single bonds to the hydrogens. So the next one I'll do a different color, red. So this is different colors, but really the same monomer. The reason why I'm doing different colors is because if it were all the same color, you wouldn't be able to say they are 5 different monomers that started out. So this is the next one is green. And this is the same thing. 2 carbons, 4 hydrogens, all single bonds. And then one more for 5. Let's do a different green. So this is 2 carbons, 4 hydrogens, and all single bonds. And there's bonds on either side that are not, you can keep those open, because what happens at the end of the addition polymerization is that you have a very long chain. You don't have 5 of these, but you might have 500 or 5,000. And at the end of the polymerization, when you've used up all of the monomers, the chains will link up. Okay, and so you won't have, this would actually be linked up like this if you have like 500 or 5,000. So that is the starting. Synthetic polymers is just called the addition polymerization reaction. Now I see a. So we started this worksheet and we're going to continue the addition polymerization worksheet, but actually want to jump down to the next worksheet and identify those big 6 plastics and write down the information from that last video. So this is, the fact is that there are 6 main plastics that you come across in your everyday. 75% of the plastics. And so plastics are polymers. They are synthetic polymers. That means made in a lab. And the idea was to mimic natural polymers like silk or wool or cotton, but then science just kind of went crazy with it. And if you can make this in a lab, what else can you make? And this is, you know, upwards of 60,000 types of synthetic polymers that range from solids to semi-solids to fabrics. And it's just, there's probably no end to it with science. They do tend to be solids that are insoluble in water. And because of both of these, most plastics float. Okay, so they are solids that can float. They're not going to dissolve in water. They don't dissolve in water, at least not easily. And that's a good thing if you're talking about a plastic water bottle. If you want to store your water in something, you want that container to not dissolve. Okay, and it should be a solid, unlike the liquid that you're storing in it. But the problem is because plastics float and they're not easily biodegradable, this has led to plastic pollution in the ocean. And it's not just one ocean, it's all the oceans in the world have this environmental issue, which is plastics that are floating in the ocean. And we'll get to that in the next one, but it's coming from the fact, the nature, the physical characteristics of plastics is they tend to be solids, they don't dissolve in water, and they float. Not all of them, but most of them. And they also don't biodegrade. They don't decompose in water. Even they don't really decompose out in soil or nature. That most of the plastic that we have, we will continue to have for hundreds, if not thousands of years. So there are some alternatives and some developments in plastic which are biodegradable, and that's good. And we'll also get to that next time. But because plastics are thermoplastic, which means they can be melted and reshaped, this opens up the possibility of recycling. So in theory, every single one of those 60,000 synthetic polymers can be melted down and shaped into a new product. That is great, except for you have some issues. You've got consumers that need to actually recycle those plastics. So I mentioned in one of the earlier videos that less than 5% of plastic is recycled. And that is in part because people don't understand what can be recycled, what can and cannot be recycled. And if I'm telling you, in theory, every single plastic, every single synthetic polymer, even fabrics like a dry fit shirt, can be melted down and turned into something else. It can be recycled. It's just that you don't have consumer knowledge, and you also don't have collection. Like some people don't actually have a recycling bin collection in their home. And then you also need the recyclers to do that. So in part of that, we will see the issue is separating out. How do you separate out the plastic so that you can just recycle this plastic number 2 separate from this plastic number 7, because they can't be melted together. So they are, in theory, every single synthetic polymer can be recycled. It's just not always done. And there also needs to be the basically the economic incentive, which is companies need people to buy recycled plastic products. And that is better than it has been, but it can always be improved. And why do people not tend to buy recycled content products? Because it usually costs more. So it's going to take some political action, basically maybe having some incentivizing companies, things, with some incentives coming from governments. So why are there 60,000 different types of polymers? Why are there 60,000 types of synthetic polymers made in a lab? Because it's so simple. It's a very simple reaction, the addition polymerization. You just need a soup, a concentration, an amount of monomers that they're all exactly the same. And then the reaction to bond them over and over and over again is most often this just simple addition polymerization. You throw in a catalyst and these monomers will bond over and over again. So starting with plastic number 1, which is called PET, or also I had in the video PETE. And this is an acronym for the longer name. And so this is actually not the addition polymerization, but this is the most common plastic. It is a clear, lightweight, and inexpensive It's also pretty durable. It's not as durable. It's not the most durable, but it's durable enough. And for that reason, it is used in water bottles and soda bottles. So your standard plastic, most commonly you're coming across is plastic number 1. And yes, that is entirely recyclable. And so that goes back to sometimes people don't recycle because there's not a recycling bin nearby. Have you ever been, with your plastic water bottle on a hike and then wanted to, get rid of it? Well, hopefully you're not throwing it out into nature, but you bring it back and find a recycling bin to put it into. That's not always the case. And so people just throw plastic into standard trash, and we'll see the fate of blue bins versus black bins versus green bins in the next lecture. But getting into the plastics that are formed from the addition polymerization reaction, this is plastic number 2. So we already looked at this. This acronym is high density, which is HD, and then polyethylene is PE. So that's HDPE. And this comes from the monomer ethylene. So notice the name ethylene is the monomer, and the polymer, the synthetic polymer, is a polymer of ethylene. So it's called polyethylene. So high density polyethylene are the ethylene chains are stacked, okay? And this will compare to number 4, which is low density or LDPE. Low density polyethylene are the polyethylene chains that are branched. So this is branching like this, and that's the reason why it has lower density, is because of the branching. You can't stack these together, okay? And so these are stacked chains of polyethylene, and these are branched chains of polyethylene. This low density polyethylene, LDPE, is also starting from the ethylene monomers. Okay, and so what is the distinguishing property of, going back to number 2, plastic number 2, is that this is also lightweight and inexpensive, but slightly more durable. So it's slightly more durable. It's still inexpensive. It's still lightweight. And it's also slightly flexible. So I showed you that bottle that was the milk bottle. And this is another bottle that I have that is, it can be clear, or this is called translucent when it has light going through it, the same with that milk bottle. And it is slightly more durable than your plastic water bottle that is for soda and water, but it's slightly more durable. So it's good for something like this, milk, or this is isopropyl alcohol. It's good for other types of solutions that you're storing in there that might need more durability because there might be a chemical reaction. So this is slightly more durable, and it's still kind of flexible. And so this, you can squeeze this one and it's not going to break. Okay. And that is useful for household containers. So it is useful for household containers, like we saw in the video, things like a squeeze bottle for mustard, or a squeeze bottle for ketchup, or a squeeze bottle for shampoo or conditioner, all those types of household containers, or even a more durable household container like liquid laundry detergent is another one I showed you. Okay. Also for milk, or any like cleaning solutions tend to be high density polyethylene. Anytime you have a liquid that you want it to be put in something that's cheap, basically, and is slightly more durable than your regular old plastic water bottle. And then this compares to number 4, which is low density polyethylene. So low density polyethylene is still inexpensive. It's still lightweight. But the number one thing about it, and I'll put this above this, it is very flexible. And very flexible means that it is like saran wrap. So it's used as a wrap. It's bubble wrap. So bubble wrap, you can blow air into it, and it's very flexible. It's saran wrap, it's flexible wrap, plastic wrap around like a sandwich, or plastic wrap around any product that you might buy. So that's bubble wrap. That's when you get a package from Amazon and there's the, that air-filled, those air-filled bubble things. That's plastic number 4. And so how often do you take that plastic and put it in recycling? Well, the thing about plastic number 4 is it requires special collection for recycling. And why does it require special collection for recycling? So even though you can melt it down and turn it into a new product, same plastic number 4, it needs to be separated out from the other plastics. And because it's so lightweight and it's so flexible, it tends to really gum up the system of recycling plants. And so for that reason, plastic number 4 needs to be collected separately. It cannot go into the regular recycling, single stream recycling. It can't go into your regular blue bin. So that for that reason also, people usually throw away plastic number 4. So when I asked you, what do you usually do when you get a package and you've got a bubble wrap in it? What do you do with that? Well, you collect it. And I take that in 3-4 times a year to special collection just for plastic number 4. So the other option, if you're not going to do that, is to actually throw it in the garbage because it does not get recycled if you put it in your blue bin. So that we'll talk more about recycling next time too. So let's talk about number 3. So going back up to plastic number 3, this is called polyvinyl chloride, and the acronym is PVC. So PVC, polyvinyl chloride, you might have heard of. It is, the monomers are vinyl chloride. And let me give you the structure of the vinyl chloride. So it starts with 2 carbons that have a double bond, and it also has the 4 single bonds like ethylene, but 3 of them are hydrogens. And one of them, to highlight, is different, is the chlorine. So that's why it's called vinyl chloride. And this is different from the ethylene monomer, and I'm going to add the structure of the ethylene monomer. It is 2 carbons with a double bond and 4 hydrogens. Okay, so the ethylene monomer down here, 2 carbons with a double bond and 4 hydrogens. You don't need to memorize that, but you will see that on the previous worksheet that we're going to get back to. And also to highlight the fact that the monomer process is the same. You start with a double bond, and in forming the polymer, you break the double bond, it becomes a single bond. So this vinyl chloride, or PVC, is very durable. In contrast to, let me spell durable, in contrast to low density polyethylene, PVC is very durable compared to the one below it is very flexible. So this is very, very, very durable. It's the strongest regular plastic. And this very strong regular plastic is used for things like pipes. So the pipes in your house that used to be made out of metals are now more commonly made out of plastic, PVC. And it's so strong it can be used for construction or furniture. It's a very, very, very strong plastic. Okay. And so this is something that you most commonly, what you actually have right now, if you have a credit card, that credit card is made out of PVC. It's something that if you've ever, need to break into a lock, you can actually use a credit card because it's such a strong plastic that it won't bend or break, or it shouldn't. So this is number 5. Plastic number 5 is called polypropylene. And so this is a polymer of propylene monomers. So let's write the name of the monomer. It's called propylene. And the acronym is polypropylene, or PP. Okay. And so here's how this monomer looks. It is 2 carbons with a double bond. So you can guess where I'm going with that. In forming the polymer, you break that double bond, and it becomes single bonds. And we'll see that again. So it has 4 single bonds coming out of those 2 carbons, and 3 of the bonds are to hydrogens. The fourth, what's different is that it has, just like vinyl chloride had a chlorine. So instead of having a fourth hydrogen, what you have here is a carbon. And that carbon is a carbon with 3 hydrogens. And so this is a monomer that has 3 carbons, a 3-carbon monomer. This compares to ethylene that is a 2-carbon monomer. So ethylene just above it is a 2-carbon monomer. There's 2 carbons, 1, 2, compared to propylene that has 3 carbons, 1, 2, 3. And so that's part of the same alkane, mother eats peanut butter. So 2 carbons is eth or E, that's the eth in ethylene. And then 3 carbons is prop or P. Okay, so there's 3 carbons in this monomer, and this was basically science, scientists said, hey, let's just change up one of the hydrogens and see if we can get a different polymer each time. And so that's what happened with the development of these plastics. So for polypropylene, this becomes a plastic that is also inexpensive and lightweight. Okay, but the more distinguishing quality about this is that it is resistant to oil. Because it's resistant to oil, this is used for food containers. So if you look at your standard takeout containers, they're generally going to be plastic number 5, polypropylene. And so this is, in general, not all food is going to have oil in it, but in advance, they figured, well, since, restaurants buy all their takeout containers, and they want to make sure that all those containers are not going to disintegrate when you put the food in, whether it's a salad that has the dressing on it with oil or not, you always want it to be resistant to oil and not decompose because of the oil. Okay, so those are food containers, usually takeout containers. And then plastic number 6. So rounding these out, plastic number 6 is polystyrene. And so this is a polymer of styrene monomers. So the monomer is called styrene, and it is PS for short. So this monomer looks a little more complicated. It is 2 carbons with a double bond. That's the simple part. And it still has 3 of the bonds to those carbons or hydrogens. Well, one of those hydrogens has been replaced with a 6-carbon ring that I'm going to draw as a hexagon. So this is a 6-carbon ring structure. So this is a 6-carbon ring. And we're going to see more of the 6-carbon ring, but for now you draw a hexagon with a circle in it. It's a 6-carbon ring with 3 double bonds in there. And this is called the styrene monomer. And the styrene monomer is unique in that it is, more complicated, but that this has 2 forms. So there are 2 forms. One is called styrofoam. Styrofoam has the air blown into it. And so that styrofoam is also used for food containers, but is used because it is an insulator. So if you want to keep your coffee hot or your iced drink cold, you will find a styrofoam cup for that. Okay, it is a food container in that respect because it has air blown into it when it's called styrofoam. And it's also used as an insulator for shock. So you can have a box that is a shipping, stuff shipped, and you find a bunch of styrofoam packing peanuts in it because of the insulator quality that you can basically have a bunch of air blown into this plastic and it will insulate from blows or shocks. Okay, so it can insulate from heat or from blows or shocks. There's also a very clear form of this. And this clear form does not have air blown into it. And so this is the crystal version, or it's the crystalline version, and this is glass-like. And so there's a version of polystyrene that is used to replace glass. So basically, if you have a picture frame and you don't want the glass in it because glass can break and it's heavy, you're going to replace it with, you're going to have a polystyrene plastic, which is very much like glass. It is clear as glass. Some glass-like containers that are fancy, like fancy candies, come in a little plastic squarish container. We'll see some of these in lab that's coming up that are like glass, and it is clear and fancy looking, and it is polystyrene. It just doesn't have the air blown in, unlike styrofoam. Okay, so let's go back to this addition polymerization reactions worksheet and fill in some of these other polymers that also form from the same reaction, addition polymerization. So we'll still have the same starting point where you have a monomer that has a double bond, and that double bond breaks and becomes a single bond in the polymer. You also need the same number of monomers go into the polymer, and you also need a reactive catalyst to get this going. And so let's take a look at the next one is polyvinyl chloride. So you are given the structure of the monomer, which is called vinyl chloride right here. And so when you are given the structure, you just need to know how many monomers. And then for these monomers that are not symmetrical, you have to understand that there are those pattern possibilities. There's the head to tail, or there's the head to head, tail to tail, or there's random. There are 3 possibilities. So in this, you are given the polymer, or so you're given the monomer. Here's the vinyl chloride monomer, and this is called not symmetrical. So you need to assign one side of it is the head and the other side is the tail. It doesn't matter which one, but you just have to decide which is the head and which is the tail. When you are given the pattern, you need to figure out which is going where. Okay, so that's why. So assign which side is the head and which side is the tail. So this is fine if I put this one, the chlorine is the head. Okay, you can decide that that could be the tail. It doesn't matter as long as you do an assignment in the first place, because when you have a non-symmetrical monomer, when it's not the same on both sides, you need to decide which side is which. Okay. And so you also are given, you want the polymer to be made out of 3 monomers. Okay, so to write this as the general reaction, this is having 3 of these. So not just N, but 3 of these. And then you will have the reactive catalyst that starts this. That's in the generic R dot. And then this will form the polymer, which has a single bond between those 2 carbons, not the double bond. So the double bond becomes a single bond. And then this is going to be exactly the same for all the rest of it. So the only thing that's different is the single bond in the middle. Everything else is the same. You have 3 hydrogens, 1, 2, 3, and then the chlorine. Okay, and so there's going to be 3 of these. So let's draw this out. This is in general what's going to happen to the monomer. But now let's put it in a head to tail pattern. So if this is the head, is the chlorine. The first one is going to be the monomer with 2 carbons and 4 bonds coming out of those 2 carbons, coming out of each of those carbons. So those are still hydrogen, 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 and this is a chlorine. So remember that chlorine is the head. So I want it to be bonded to the next monomer, which I'm going to do in a different color, purple. I want it to be bonded to the next monomer as 2 purples, and then the tail. Okay, so what is the tail of the next monomer? The tail of the next monomer has to be a hydrogen, is the tail. So this tail that it's bonded to is a hydrogen there. Okay, and so that means the rest of it are the hydrogens, and then this is the head of that. Okay, so the head of this purple is needing to be bonded to the next monomer, which I'll do in a different color, red. Okay, so those 2 carbons have a single bond between them, and then the rest of it are those 4 bonds. There are 1, 2, 3, and this is the tail is the hydrogen. Remember, tail is the hydrogen. And so that means the chlorine is on the other carbon. So that's a head to tail pattern. And there's 3 monomers, 1, 2, 3 in those different colors. Okay. And so in theory, you wouldn't just have 3, you'd have hundreds of these, and then these would link up at the end. So you can leave these open. You can leave this open on this end and open on this end, or in theory, you'd have a whole bunch and you'd link them up like that. Okay. So that is when you have a non-symmetrical monomer, which is polyvinyl chloride. And this polypropylene is also starting off with a monomer. You're given propylene, and it is not symmetrical. It is not exactly the same on both sides. This is assigning one side has to be the head and the other side has to be the tail. So this assignment, this time, the CH3 group, the different part, is going to be assigned the tail. So that's what I mean. You can decide either side can be the head or the tail, but you do have to make that decision. So you need a polymer composed of 4 monomers. So I need 4 of these in the head to tail pattern. So this is going to be a reaction that needs the reactive catalyst. And then in general, what happens to the monomer is that double bond breaks and becomes a single bond. Okay, so I'm going to have 4 of these. So I'm going to put a 4 subscript, and everything else stays the same. You have 3 hydrogens, and then 1 is a CH3. Okay, so that needs to be inside of the bracket. So what this looks like is you're going to have 4 of these monomers. So starting with the first one is 2 carbons with a single bond, all single bonds. And this having a head to tail pattern, well, this is the head of this one is hydrogen. Okay, so this is a hydrogen that is my first monomer. Okay, and then the rest of it, this is the tail of it, needs to be the CH3. And then those are hydrogens. So you have 3 hydrogens and 1 CH3 on that first monomer. But I want it to be connected to the second monomer, which I'll do in a different color, the tail of the second monomer. So first, let's draw the skeleton of the second monomer, which is 2 carbons, and then single bonds coming out of those carbons. So the tail of that, bonded to the tail, means I need it to CH3, because remember, we assigned CH3 as the tail. So the other bonds are 2 hydrogens. And then a third monomer, choosing a different color, is 2 carbons with all single bonds. And this is the head of this was purple. All right, this head is purple. And then the next monomer needs to be connected to the tail because it was a head to tail pattern. Now it doesn't have to be head to tail. You can have head to tail, or you can have head to head, tail to tail, or you can have random. All right, so you'll see that in, so this is the tail is the CH3 group, and then those are all hydrogens. And then the next is a different color. This is the 4th monomer in green. So 2 carbons with single bonds. The head of this red monomer is that hydrogen. So I want it to be connected to the tail of the green monomer. And this is, the tail has to be a CH3. Okay, so the rest of those are hydrogens. So 3 hydrogens and 1 CH3. So you would have, in theory, hundreds of these or thousands of these, and then they would link up at the end. Okay. So that is the 2 examples of the monomers that are not symmetrical, and you can have the patterns for the polymer formation. So this is just some of the 60,000 types of synthetic polymers that we have. So taking a look at the monomers, okay, and basically trying to test yourself here is how are these 3 monomers similar to ethylene? So remember, ethylene was the starting monomer that we looked at in the addition polymerization reaction. So ethylene is 2 carbons with a double bond and then 4 hydrogens. So these all are similar. They all have a double bond. So that carbon-carbon double bond, which in the addition polymerization reaction breaks and becomes a single bond. So how are these different from ethylene? So ethylene is the only having the 4 hydrogens. Well, how are these different? Is that you either have all the hydrogen atoms replaced by a different atom? No. All of the hydrogens replaced by chlorines, or one or more of the hydrogens are replaced by a different atom. That's your correct. So you don't have all the hydrogens replaced. You have one of them replaced here, 2 of them replaced here, and all 4 of them replaced here. But all of these represent monomers that are present in polymers now. And so that's what scientists did. They said, hey, the starting point is 2 carbons and 4 hydrogens. What happens if we vary the atoms that are bonded on there? We can form polymers with different physical characteristics and therefore different uses. Okay. So let's take a look at the different types of polymers. There are up to 60,000 of them. So polyvinyl chloride is the vinyl chloride monomer. So here's one vinyl chloride monomer. It has the 2 carbons with a double bond and 3 hydrogens, and one of the hydrogens is replaced with a chlorine. So let's move on. And so that's one monomer, and we're going to build this with all 5 of these. So notice what happened though, is that this monomer no longer has the double bond in there, that there are all single bonds. The double bond breaks to allow for bonding on either side of the monomer. So in adding the next monomer, you will find this is called the addition polymerization, is the addition of the monomer has to happen only on one side of the polymer chain. So this had the adding the second monomer, you saw the double bond is now a single bond, and adding the third one, same thing. And so the pattern here is the head to tail pattern, where each monomer has a repeating pattern there. So this is, I'm going to show you what happens when I try to add the 4th monomer to this side. What happens when I try to add it to the left side? Because remember what I said about addition polymerization is you can only add to one side. So what happens when I put this over here? It goes and runs over to the other side. And that's because in what's stuck to this side, you can't see, is the reactive catalyst is stuck to this side. And so at the end of this reaction, the reactive catalyst pops off, and then you can link both ends. So this again, try to stick it on this side. It's not going to work. It only adds to one side. And so this is what's formed here from this non-symmetrical monomer, is a head to tail polymer. And so there's overall 5 of these, but in theory, you would have hundreds or thousands of the monomers, depending on how many you added in there or how many go into the polymer. Okay, so let's take a look at this other saran wrap. So if you have saran wrap, that's a very flexible plastic, and it starts with this monomer. So there are 2 carbons with a double bond and 2 chlorines. So just varying the 2 chlorines, you end up with saran wrap compared to polyvinyl chloride. So let's pull this down here. And so the addition polymerization is you take the monomer and you add it to one side. So see here, I'm going to try to add it. Always adds to one side. And this is the overall chemical reaction, is 5 monomers go into the polymer. The only difference you see is the double bond is now a single bond. And it's not usually 5, but hundreds or thousands of monomers in the polymer. And you end up with the physical characteristics of saran wrap just by having 2 chlorines in the monomer instead of 1 chlorine for polyvinyl chloride. And so let's look at this last one, which is Teflon. So Teflon coating on a metal pan is these chlorines. Sorry, these are not chlorines now, these are fluorines. And that's why there has been some issue with Teflon coating. When Teflon coating degrades, you end up having fluorine incorporated into the food you cook in that pan. And some fluorine is tolerable. And in fact, studies show that no matter what, even if you don't have Teflon pans in your house, you have fluorine in your body, because Teflon is used in industrial applications. So food that's cooked that is processed. So if you buy, a Twinkie, it was made in a Teflon coated pan. or, at the industrial level, whatever they call the thing that they cook Twinkies on. And so you are exposed to fluorine, whether you like it or not, even if you cook if you cook things, everything in the house. That's possible that you are not exposed to fluorine, but how you're exposed to fluorine is because Teflon will break down over time, and small amounts of the fluorine end up in the food you cook. Now, it's not anything to be afraid of, unless you really have a lot of, I'm not sure I've ever heard of fluorine exposure affecting anyone. So here's building the monomers one at a time. You break the double bond and build this polymer. So there are 5 of those monomers. Now, this is an example of a symmetrical monomer. And so it doesn't matter here for the assignment of head to tail when everything is the same on both sides of the monomer. So this is 5 of these monomers in the polymer, but most polymers, you'll have a lot more than 5. So all of the monomers go in to the polymer, usually in the thousands, and you end up with this, which is not a solid, but it is a Teflon coating that is added onto these metal pans. Okay, so that's what I have. Let me